we're going to be solving a lot of trigonometric equations, and some of them will get a little complicated. So here are some tricks to help you move forward when you start to get stuck. First of all, never divide by functions. Always use the zero product property. What do we mean by this? Well, suppose you have the equation sine of theta times cosine of theta equals sine of theta. Some students will see this and divide by sine of theta and cancel that out. If you do that, you run the risk of dividing by zero because you don't know what value theta is. Maybe the sine of theta is equal to zero, and then you divide by zero, and then you've messed everything up. So instead, what you want to do is you always want to try to move towards factoring. Sine theta times cosine theta minus sine theta equals 0. And then use the zero product property from here. Because now when you do the factorization, you will have the explicit case, sine of theta might be equal to 0, which doesn't happen if you go from here and try to divide. Here's the next tip. Minimize the number of functions through substitution. You might have a situation that looks like this. Cosine squared theta plus sine theta is equal to 0. Now, what you're going to do is, if you see this, you have sines and cosines. You can't really do a factorization because you don't have the same terms here. And so what you can do is you can use the trigonometric identities. In particular, you want to be using the Pythagorean identity here, which is if you have, let me squeeze it up here, sine squared theta plus cosine squared theta equals 1. Right? You can actually use this to write cosine squared theta in terms of sine squared theta. So if you subtract sine squared theta from both sides, you get cosine squared theta is 1 minus sine squared theta. I'm sorry for squeezing it in there. But then that becomes a substitution to here. And now you have just one trigonometric function, and now the factorization will work. And the last one is to look for differences of squares. We're going to run into things like this, 1 minus sine squared theta a lot. And it's important to recognize that this is a difference of squares. This is 1 squared minus sine squared, which can be written as 1 plus sine theta times 1 minus sine of theta. And this will come in handy many times when you have fractions and things like that where you're looking for something to reduce. Look for this type of pattern. It'll come up more often than you think. And so here are some quick tips, and we'll go to an example. Here's an example. Solve 2 sine squared t minus cosine t equals 1 on the interval from 0 to 2 pi. So we can see we have a mixture of sine squared and a cosine, and using a Pythagorean identity, we can replace the sine squared with a cosine squared. That will get everything down to a single variable. So I'll go ahead and write out that work again. Sine squared t plus cosine squared t equals 1. And we're trying to solve for sine squared because that's the thing we want to replace. So sine squared t is equal to 1 minus cosine squared t. Now when we make this substitution, we're substituting for the sine squared. So 2 times whatever sine squared is, which is 1 minus cosine squared t, minus cosine of t is equal to 1. So now we have everything down in terms of a single variable. But we need to move towards trying to look at some sort of factoring technique. And so we need to get the right-hand side equal to 0 so that we can use the zero product property. We'll first distribute 2 minus 2 cosine squared t minus cosine of t equals 1. Typically, we want the cosine squared term to be positive, the square term to be positive. So we can either multiply by -1 or just move everything to the right-hand side, which is what I'm going to do here. So 0 is 2 cosine squared t. We're adding plus cosine t. And then we have this 1, but then we're going to subtract 2. So -1. And now we have to factor. Factoring requires us to use potentially either the quadratic formula or the AC method of factoring, whatever method of factoring you're comfortable with. I actually prefer the AC method because it handles situations that you have non-monic polynomials, meaning that the square term has a coefficient other than 1. And so that works for here. So what does the AC method say? So we're trying to find, you can think of this as 2 times x squared plus x minus 1, if that helps you see this a little bit more clearly. Sometimes students get confused because there's so many terms here. This is just cosine squared, and that's just cosine. So you can think of it that way. So anyway, the AC method. Whoops. The AC method. What does the AC method says? We're looking for pairs of numbers that multiply to the product AC and add to the value B. So what does that look like for here? Two numbers that multiply to, well, 2 times -1, -2, and add to +1. And now we just have to check, what numbers can we think of that multiply to -2 and add to 1, if any? What pair of numbers works? And so we can see that +2 and -1 is such a combination. 2 times -1 is -2, and 2 plus -1 is +1. And so this helps us to factor. I'm going to bring this down. So 0 equals 2 cosine squared t. This middle term right here is going to be broken up with coefficients, with these coefficients. So we will have +2 of this and -1 of that. So +2 cosine t minus cosine t minus 1. Now this feels a little bit like magic, but basically what we've done here is we've just taken this middle term and we've rewritten it. If we were to combine these together again, 2 cosine minus 1 cosine is 1 cosine, and that's up there. And the point of doing this is it allows us to factor by grouping. So here there's a 2 cosine of t that can come out, and we're left with a cosine of t plus a 1. Over here that's negative and that's negative, so minus cosine of t plus 1, right? So the minus distributes to make that there. And here's where you know if you've done your factoring by grouping correctly. You should have a term in parentheses that is identical. So we have 2 cosine of t minus 1, so that's that minus 1 from that minus sign, and both of these are being multiplied by cosine of t plus 1. And here's where we can use the zero product property. We've now got this times this is equal to 0, so one of these two things must be 0. We're out of space here, so I'm going to erase the board and give myself more space and pick up from there. Okay, so here we are with 0 equals 2 cosine t minus 1 times cosine t plus 1. And by using the zero product property, we're going to set each of these equal to 0. So 2 cosine of t minus 1 is equal to 0. Or we could have cosine of t plus 1 equals 0. So we'll just focus on this side for a moment. What's going to happen? Well, we're going to isolate the cosine of t term, so cosine of t, add 1, divide by 2 is 1/2. And we have to solve this equation. And this pulls back to what we were doing in an earlier section. Let's take a look at the unit circle picture. The cosine function corresponds to the x-coordinate, and we want the x-coordinate to be positive 1/2. So we're looking at a situation where we have solutions in quadrant 1 and quadrant 4. What is the reference angle going to be? Cosine of which angle from 0 to 90, or from 0 to pi over 2, gives us 1/2. And so with a little bit of thinking, and you should be able to find that the reference angle is going to be pi over 3. And so we use that information to help get our t values. Now in this case, because we're only interested on the intervals from 0 to 2 pi, we're not going to worry about the coterminal angles. So this first one is going to be pi over 3. What are we going to get for the second one? Well, for the second one, to get in the fourth quadrant, we have to go all the way around and then subtract off the reference angle. So 2 pi minus pi over 3, which happens to be 5 pi over 3. So these are two solutions so far. And then we have to jump over here and look at the rest of this. So cosine t is equal to 1, or sorry, cosine t is equal to -1. What's this going to look like? Once again, focus on the unit circle picture. The cosine is the x-coordinate, and we want the x-coordinate to be -1. But since this is a circle of radius 1, we know that's going to be that point. So in fact, there's only going to be one solution from this part. T is equal to pi, and that comes from just looking at the picture. And so in all, we have 3 possibilities for t. T is pi over 3, pi, or 5 pi over 3. And again, we don't have to worry about coterminal angles because we're asked to solve this on a specific interval. So here's another example. Solve 3 tangent t is equal to sine of t. Now if you look at this, a Pythagorean identity is not going to help us here because it relates sine to cosine and tangent to secant, and those two things aren't interacting. So that's not the right substitution here. And so you have to kind of just work through what other possible substitutions you can make. When in doubt, you can always try to get everything in terms of sines and cosines. It's not always the best move, but it's just something that you need to have in your arsenal of tricks. So 3 sine of t over cosine of t equals sine of t. Well, we had a fraction, so we might as well clear the denominator, multiply both sides by cosine of t. And here's a place where, again, students can run into problems. Don't divide by functions. You might be dividing by 0. Instead, move towards factoring and using the zero product property. So let's move everything over to the left-hand side. 3 sine t minus sine of t cosine of t is equal to 0. There's a sine term in each of these, so we'll factor that out. Sine of t times 3 minus cosine t is equal to 0. Right? So now we have a product of two things, sine of t and 3 minus cosine t equals 0. We use the zero product property. Either sine of t equals 0 or 3 minus cosine t equals 0. Well, this one's already in a form where we can look at the unit circle. Sine of t, sine is the y-coordinate. We want the y-coordinate to be equal to 0. And so that's going to give us those two intersection points, which happen to be at 0 and at pi. In this case, there's no restriction on the domain, so we're just going to get all of them. So t is equal to 0 or pi. And then we have to remember plus 2 pi k, the coterminal angles. Add multiples of, integer multiples of 2 pi. Where k is an integer. Now the book will sometimes simplify this just so that you're aware, because if you actually take a look at these values, I'm going to squeeze that in right up here. 0, 2 pi, 4 pi, 6 pi. That's from this top one. From the lower one, you get pi, 3 pi, 5 pi, and 7 pi. And so with this, you can see that we're actually getting all the integer multiples of pi. So the book will sometimes condense this into a single answer that will look like 0 plus pi k. I find that a little confusing, so I tend to leave it in this form just to remind you that this is coming from two separate solutions. But just be aware that that might happen sometimes in the solutions. Over here, let's solve for cosine of t. Cosine of t, we're going to add it to both sides, is equal to 3. Now this is a different situation. Cosine of t equals 3. Cosine is still the x-coordinate, but we want the x-coordinate to be 3. But if this is a unit circle, equals to 3 is way out here somewhere. What does that mean? That means that there are no solutions. No values of t will get you a point that is the intersection between this line and that circle. So there are no solutions from this part, which means that all your solutions are down here. And this is another example of using factoring to solve.